The ground moves, not a tremor, not a rattle. A full seismic event, the kind that liquefies soil, collapses bridges, and sends century-old buildings into rubble in under a minute. And in the middle of all of it, a 500-meter glass and steel tower sways. Not cracks, not crumbles, sways. Back and forth, several meters in each direction, like a reed bending in wind. And when the shaking stops, it is still standing. Every floor intact, every window unbroken. The people inside barely needed to evacuate. What you just imagined is not a hypothetical, it has happened. It is happening in cities built on fault lines, right now. And the reason those towers survive while smaller, older buildings collapse comes down to one of the most counterintuitive principles in structural engineering. Rigid things break. Flexible things survive. Here's what an earthquake actually does to a building. The ground shakes horizontally, side to side, not just up and down. The base of the building moves with the ground, but the top, due to inertia, wants to stay where it is. This creates a shearing force trying to tear the building sideways at every single floor simultaneously. The taller the building, the greater that force at the top. A rigid structure fights it. And in a large enough earthquake, the force wins. The structure cracks, the connections fail, and the building comes down. Engineers understood this problem long before they had solutions for it. The breakthrough came gradually, through the combined work of seismologists, structural engineers, and material scientists across the 20th century. The modern approach does not try to stop the building from moving. It controls precisely how the building moves, and in which direction, and at what speed. The first tool is the moment-resisting frame, a rigid grid of steel beams and columns welded at every joint that absorbs lateral forces and distributes them across the entire structure rather than concentrating them at any single point. When the ground shakes, the frame deforms slightly, but it deforms as a unified system, bending rather than breaking at any one place. The second tool is the shear wall, a solid reinforced concrete panel built into the core of the building and running vertically from foundation to roof. Shear walls act like a stiff backbone, resisting lateral movement and transferring horizontal forces directly down to the foundation. Most modern skyscrapers combine a rigid concrete shear core with a flexible outer steel frame. The core holds firm while the exterior absorbs and disperses the energy. The third tool is base isolation. Instead of connecting the building directly to the ground, engineers place it on a series of layered rubber and steel bearings between the foundation and the structure above. When the ground moves, the bearings absorb and deflect the horizontal motion before it can reach the building. Researcher James Kelly at the University of California, Berkeley, demonstrated that base isolation can reduce forces transmitted to a building by up to 80% during a major seismic event, a reduction that is the difference between standing and falling. The fourth tool is the tuned mass damper, a massive counterweight, often hundreds of tons of steel or concrete, suspended inside the upper floors on hydraulic arms or pendulum cables. When the building sways in one direction, the damper swings the other, directly counteracting the movement. The Taipei 101 tower in Taiwan contains one of the most famous examples, a 660-ton steel sphere, 6 meters in diameter, suspended near the top of the building on steel cables. During earthquakes and typhoons, it swings visibly up to 100 centimeters, absorbing energy that would otherwise transfer directly into the structure. Engineers built glass observation windows specifically so visitors can watch it move in real time from the floors below. The foundation is the final piece. Soft sedimentary soil amplifies seismic waves dramatically, a phenomenon that caused catastrophic damage in the 1985 Mexico City earthquake, where buildings on the ancient lakebed suffered far greater destruction than those on solid rock nearby. Modern skyscrapers drive foundation piles 50 to 70 meters deep into bedrock, bypassing the unstable upper layers entirely and anchoring the structure to ground that cannot be shaken loose. Every one of these systems works on the same underlying logic. You cannot stop an earthquake. You cannot build something strong enough to simply resist one. What you can do is design the building to move with it, to bend, absorb, redirect, and dissipate the energy rather than fight it head-on. Rigidity fails. Controlled flexibility survives. So the next time you look up at a glass tower in a city built on a fault line, it is not standing despite the earthquakes. It is standing because of everything engineers learned from them.